Hello, hello, it is time for lecture 20. Lecture 20, or if your video is flipped, lecture 20, or maybe my video is flipped, lecture 20. Hello, 20. It's so good to see you. Thank you so much for being a part of this. I'm very excited to move forward and tell you more about quantum mechanics. And from there, right, this thing that's starting to get spooky, a little bit weird, right? And then we're going to zoom into the stuff that comes back to reality. How the quantum world, how quantum physics, not that quantum realm from Wasp and the Ant-Man, right? I'm just saying, but the quantum thing, right? The fact that quantum mechanics, the quantum physics is a reality that underpins all the little things about stuff. We're eventually talking about the atoms and molecules that make up us. And that stuff leads to the next aspect of the realization, wow, what we're made of. We already know a little bit about the standard model, right? But there's more, all how it sticks together. It's so amazing. Can't wait to tell you all about it. Here we go. This is going back. We'll revisit for a second, just remind ourselves about the uncertainty principle, right? The Werner Heisenberg thing. Remember, I was messing around in the envelope about oh, should I make it about or greater than or equal to or greater than, or just kind of a little joke about the fact that we're uncertain, right? Well, let me write down for you here. This is the I've written on this piece of paper here the actual formal, and again, uncertainty, right? So who cares? But it's the formal explanation of the uncertainty principle where we have, remember, it's about H, and it's actually the formal definitions, if you want to do it that way, right? And you may have seen this in the textbook if you did some of the extra reading in chapter 29, that the energy uncertainty, the uncertain amount of energy that's encapsulated, right, in contained in any time interval is always less than Planck's constant divided by 4 pi or equal to it at most, right? At the same point, if you're trying to figure out within a certain position, right, where exactly are you in space, given a certain amount of momentum that you have, how much mass or velocity or whatever that you have, the momentum that you have, that's also less than or equal to Planck's constant divided by 4 pi. Okay, so this is kind of the formal mathematical way of expressing the uncertainty principle. But everything we talked about in the previous lecture, basically saying that uncertainty, right, this sort of at the basic, most microscopic level, there's still a lot of stuff that you can never measure. No matter how hard you try to measure carefully one thing, the other thing will just become less and less certain. That's just kind of how it goes. So that's just a really interesting aspect about physics. And then that matter thing about waves and particles. Remember that wave-particle duality? We've been dancing around that subject ever since we started talking about light and electromagnetic radiation, right? Well, now's the time to hit it hard and get it real for something that we're really trying to understand. And so I'm going to write that next part down. It basically hinged on a guy, okay, named Louis de Broglie. Prince Louis de Broglie, French dude. And if you read chapter 29.6, there's actually an explanation about that. We might jump on that a little bit and share the screen a little bit. Wow. But basically what happened was that this guy, Louis de Broglie, okay, basically said, you know what? I can show mathematically that matter has waves, okay? Or more specifically, particles. At that time, it was still not 100% certain whether particles could be massless, right? We knew that photons existed, but there was still a question, well, photons are massless, but what can they actually do? Are they actually just, because they have no mass, they just have no effect? Well, we know they carry energy, but what's that point, right? So matter waves, or more generally, particle waves, is what this guy Louis de Broglie was working on, all right? And so this is de Broglie, the guy's name. It's spelled, it looks like de Broglie, but he's French, so it's de Broglie, like that. Interestingly, I think there's another de Broglie. I believe his older sibling was also a physicist of some renown. And so Louis was a young guy in around 1923 when he sort of said, hey, you know what? I think that we can make an equation that very simply explains how much matter or what the particle waves are depending on its momentum, so that the wavelength of any particle, lambda, right, is Planck's constant, there's that number again, divided by the momentum of the particle. Okay, the momentum is usually mass times velocity for massive particle. What about massless particle? As it turns out, in an interesting approximation that we can use, it's the momentum times the speed of light for a photon. But you can't just put that in there because photons are massless, and therefore you have this weird, you have to do a little bit of interesting, strange mathematics to it, which is kind of cool, but beyond the scope of what you need to know for this course, because what we're talking about is the coolness of this aspect of things, right? The wavelength of a matter wave or a particle wave is the Planck's constant, right? This number, 6.63 times 10 to the minus 4 joule second, divided by the momentum of the particle. Whoa, that's pretty cool. I'm going to write that down a little bit here. I'll just label these things. Wavelength here, okay, is Planck's constant, again, divided by the momentum of the particle. And this is cool enough that I'm going to put a little box or a circle around it so that you remember it, because this is really, really key. That explains how you and I are shimmering in light too. It explains how an electron shimmers, like the wavelength that it has. Me, I have a wavelength. You have a wavelength. That's pretty cool, right? Yes, it is. And that wavelength is determined by this equation. Now, let's be real. My wavelength is tiny because my momentum is huge, right? As an example, like right now, if you want to look on the grandiose scale of things, I am sitting on the Earth, right? And the Earth is moving around the sun at 66,000 miles per hour. Yes, if you're taking astronomy, you would learn that cool stuff too. And I'm happy to share that with you someday, because that's great, fun stuff about the solar system and the universe and things like that. But never minding that aspect of things, for now, I am moving at 66,000 miles per hour, and my mass is, really big, right? Compared to an electron, since it's like, somewhere around 50 to 100 kilograms in that sort of space in the middle. So my wavelength, 10 to the minus 34-ish up here, right? And then in terms of meters per second, I'm traveling, probably like 30 meters per second. So what's, 10 to the minus 4 divided by 30 is like even smaller, like 10 to the minus 35 to the minus 36, and I multiply that denominator by my mass. So my waves are much, much, much smaller than light waves, right? So me as a particle, my waves, unnoticeable, right? You can't measure it using any kind of current modern technology. But let's say you're an electron, right? And your mass is very small. And if you're not moving very fast, then your wavelength, the wavelength of an electron, could be quite large, right? Pretty cool. And so how do you measure that? Well, you have to just think about how to do it and then use other technologies to get an inference, maybe through interference patterns. Oh, remember those? We're talking about waves, right? When you drop one pebble into a pond, right, it makes nice circular waves going out. If you drop a handful of pebbles, and you get all these different waves that are kind of superimposing and interfering with one another. So you wind up with a mess, a jumble of waves and partial waves and waves this and that, right? And you can add strength to waves, or you can kind of make them so chaotic as to like cancel out the power or the amplitudes of the waves. So you wind up with a sort of a flat-ish surface, right? So in the end, instead of having lots of big wave coming out, you wind up having like a whole lot of little waves that just wind up canceling each other. And you have a pond that's just chaotic on the surface, but not really wavy, right? So that's the kind of thing that can happen. That Louis de Broglie figuring out that matter waves or particle waves are like this. Now, interestingly, you can go in the other direction. And what happened was right around the same time, like 1923, that this guy Louis de Broglie was doing this, there was another scientist named Arthur Holly Compton. Okay, Arthur Holly Compton. This guy Compton was like, hey, check this out. The momentum of a light particle, right, could have to do with the wavelength of the light particle. Wow. So that is really interesting, isn't it? Because what he basically said was that the wavelength of a particle, let's say a photon or anything, right, has a certain mass, right? If it's like got some sort of wavelength to it, then there is a space within which, right, there is no information. It's kind of like the fundamental or the wavelength of the thing that of the little tiny particle that's moving around. And so that became known as the Compton wavelength. All right, so I will write that down here. You take this, right, and you basically just kind of switch it around a little bit. You take this P, right, this is the matter wave, and you convert and you realize that this P here, right, is if it were massless, if the object were massless, and you wind up with a momentum of a photon or something like that, because photons are massless particles, right? You wind up with this really, well, what can I say? Let's just do it this way. We'll call it the Compton wavelength. The Compton wavelength. I'm going to write it kind of a little bit over here. Just look, it's going to be very similar to the H over P for the matter wave, but this is not necessarily matter, but it's rather the P kind of converted for a circumstance with or without, you know, a photon, because a photon has no mass, but a particle with mass. So you go lambda equals H over MC, like that. Okay, so MC and P, well, you know, can you say that the photon, that the momentum of a photon is its mass times its C? Well, the photon doesn't have mass, so no, you can't say that. But as it turns out, this is a really interesting kind of coincidence almost. And if you take these pieces of information together, right, you have the matter wave particles, and then you have the Compton wavelength of something, like where the information, what is the fundamental wave length of a particle or something like that. See how that goes? This sort of the minimum length within which there is information outside, and then inside you can't really figure out what's inside going on. You take that quantum mechanical thing, a little bit confusing, yes, but bear with me, because now I'm going to go to the computer and go to the textbook to section 29.6, right? You see the de Broglie wavelength, and then we talk about the Compton wavelength, which is kind of further up here, 29.4, and then we go to wave particle duality, Heisenberg uncertainty principle. If you've read all that stuff, great. But now I want to take you to chapter 30 and atomic stuff. Okay, this is great stuff. And we've already talked about some of this earlier in the semester. Remember, we're talking about matter and energy and particles and stuff, right? But now take a look at what happens if we take that information, the de Broglie wavelength and the Compton wavelength, right, over here, momentum of photons and things like that, right? You get here, the wave nature of matter causes quantization. I know it sounds silly, but you know, what does it mean really? Here's what it kind of means. Ready? We were talking about waves before, and sometimes waves, well, if you have, like I said, the handful of pebbles, or if you have one pebble, if you drop a bunch of pebbles sort of in exactly the same sequence, you can get different areas where you have lots or you have only a little bit of wave action, right? And so if you have a strong wave action, like a wave representing an electron, then that's an area that you can actually have the electron exist in an atom, right? Whereas if you have some sort of situation where you have this constructive interference, then you wind up an atom and the electronic can be there in the electron, in the atom. All right, read this to your extent that you're interested. But let me give you the point, okay? Look, there are certain areas in an atom where the electron orbiting around it can exist. In other words, constructive interference of that wave allows for the existence or the location of those electrons in those parts of the atom beyond the nucleus, right? If they don't do a good job of constructively interfering, then they can't be there. All right. So atoms, when they have electrons orbiting around them, basically only have certain energy levels or certain positions where the electrons can stay. They jump around as a result. When they're in other parts where the waves are interfering destructively, those parts of the atom are parts where the electron cannot be. On the other hand, if they are constructively interfering as waves, then those are areas where the electron can be. So way back earlier, we were talking about the orbitals of the atom, right? Back when the Ernest Rutherford, we're talking about the Rutherford atom from a long time ago. I'm going to use the back end of this to sort of remind ourselves of what that looked like, right? We had, whoops, I better grab that. There we go. Okay, so we had a circumstance where you have an atom, right? You have the nucleus in the middle. And then you have levels where the electron can go, right? Now, when you take chemistry, if you take chemistry, then you will wind up hearing about like energy levels and atomic or nuclear or electron shells, K, L, M, etc., and things like that. Okay, so you should know those things because those are fun. But what we're talking about here, which is similar but different, right, is that there are certain energy levels around the nucleus where the electron is allowed to exist, not just those shells that we're referring to earlier. That's a structural type thing, but this is an energy type thing. So around the nucleus, the electron or electrons that can move around at different energy levels. Okay, so those are energy levels, not K, L, M shells, but something similar. So these are energy levels. So the electron doesn't have to be at any given energy level at once. So it can be here, it can be here, it can be here, like that. Okay. These are energy levels where the electron could be. So if an electron is, say, down low here, okay, it doesn't have a lot of energy, it's kind of in this energy level, and then a photon hits your atom, doink, the electron could move. If the electron absorbs the right amount of energy from the photon that hits this proton, let's say photon hits this atom, and if the right amount of energy in that photon hits this atom, then the electron can move to this spot, right? Or to that spot. Later on, if that electron has a lot of energy and it loses some energy, the energy kind of goes away somehow, then it can go down to this spot or to that spot. But because those are the places where you have constructive interference of the waves, those are places that are allowed, the spaces in between are not allowed, which means you're jumping from one level to the next, right? Which means you can't necessarily find electrons in the middle. You don't just get electrons randomly in these different positions, okay? So you have to go from one quantum of energy to another quantum of energy. The amount of energy absorbed from light coming in or energy hitting this thing has to go from step to step to step, right? Remember when we're talking about heat, same thing. If I take another atom and it bumps this atom and it absorbs a certain amount of energy from that collision, the amount of energy can absorb only can go on these steps, right? This energy level or that energy level or that energy level, these steps are tiny. So if you're talking about a huge like room full of gas or something like that, no big deal, right? You can't really detect it, but that's how the energy moves back and forth amongst these atoms and molecules. So this thing can zip around, right? This is going to be jiggling and vibrating and everything, but the electrons, if they absorb or anti-absorb, like give up energy, then they can only go from one step to the next to the step. These steps are quantized, okay? They're quanta of energy, and therefore the term quantum mechanics. So quantized, right? That's what we saw earlier, quantized energy states. quantized energies. So in an atom or a molecule, you can only have certain, not an infinite number, but certain levels of energy for which your electrons in that atom or molecule are allowed to live. All right, so that is the result of quantum mechanics and the wave and the particle duality and all that. It's really kind of cool. What is the result of that? You may have seen this before in the previous lectures in the class too. That's 30.7, right? Patterns in spectra. When you look at the light that's coming through like a prism or something like that at this from the sun or something like bicycle wheel, the little sphere, like the geometric optics type stuff that Isaac Newton did, right? You basically find lines. The lines of the light that come out, there's a smooth light that comes out, and then there are lines of individual light that comes out. And so if you can look at different atoms and molecules, you actually see different lines of light coming through, right? The electromagnetic spectrum, remember we were talking about that earlier, right? This is where you wind up seeing these different lines. And as a result, you can wind up detecting individual atoms or groups of individual kinds of atoms based on the kinds of light that they emit and absorb. Each atom or each type of atom has a barcode to some extent. The lines of light, the photon energies that can come out of them or can be absorbed by them are very, very clear. And millions or billions of trillions of these kinds of reactions can happen at every second, every fraction of a second in a big cloud of gas. And together, all those little photons come out and show colors of light that are visible to our eyes. That's spectra. Man, that's amazing, right? Hang on just a second. I'll be right back. Hold on. Pause this. Okay, I'm back. Sorry for the interruption. Of course, for you, there was no interruption because I paused the recording, but nevertheless, thank you. Okay, so let's get back into the flow of things. We're talking about atomic spectrum, right? Basically, you have an atom, and because it has all these different energy levels, right, the amount and the colors of the light can be absorbed or emitted specifically at those colors. And so each kind of atom or molecule has its own barcode that you can actually figure out what kinds of energy levels they are. If I share the screen here, I'll give you an example. We'll go back to this patterns in quantization, which we'll get back to in a second, but this textbook, very useful in some information. Let me show you the pictures, right? If I take a blob of light, take light from the sun, for example, and it's coming through at me, it will have this continuous spectrum, like because the sun is a hot object and it glows in all the different colors of the rainbow, all the different spectra are filled. Now that's because this thing, right, has millions, billions, trillions, quadrillions of different atoms. And all those different atoms and molecules, all the different energy levels are filled in because there's so many of them, and the heat of it causes all the energy in the different atoms and molecules to sort of mix. The atoms and molecules are colliding, all that photons are coming off of all this system, all different wavelengths, right? But if you only had, say, one kind of atom or molecule in that system, right, and it were kind of spread out, so you don't have a lot of collisions and so forth to smear out, sort of like you don't have a lot of pebbles dropping into your ponds, you're smearing out all the light, but you have specific like gas that shows individual objects, individual atoms and molecules able to emit their own light or absorb their own light. This is what you get, right? You basically have, say, in this case, a lot of gas in this emission spectrum, and the lines are bright where those barcoded lines of those atoms are shining light. And in this absorption spectrum, what happens is that you have a warm background where you have lots of light coming through, as with the continuous spectrum, but the cooler gas on the surface, or say surrounding the hot object, say interstellar gas around a star, or say fog that might be around a light bulb or something like that, wind up creating these lines of absorption, because that's where the cooler atoms with lower energies are able to absorb the light coming out, right? So that's sort of how you're winding up doing this. To do a little extra thing, you get an emission spectrum when you have high energy gas and they're dropping down different lower energy levels. And each time it drops down in energy level, there's a particular wavelength of light, or a particular photon of a particular energy that comes out. And so if you add up those in the millions or the billions or the trillions or the quadrillions, and you get a bright line at that location, right? And the other direction, an absorption spectrum, if there's already energy out here, but what happens is that these electrons are closer into the atomic nuclei, and then they jump outward. They get quantized out to individual locations depending on whether or not they're absorbing the photons of just that wavelength or of just that energy in order to create the spectrum. Okay, so when you have absorption, things are going from in to out, the electrons, right? And then the photons are being absorbed. And the amount of energy is being absorbed at just the right wavelength for the photons. And if you have an emission line, you have this high energy gas that's dropping down and then is emitting those photons. Yeah, pretty cool, right? I know it seems so abstract, but it is the way that we see. It's how light is produced. It's that kind of energy exchange inside atoms and molecules from the electrons bouncing back and forth that allow us to see, that gives us all of our electromagnetic radiation in the spectra of the objects that we see. Now, in a way to analyze these, you don't have to just do these kinds of pictures. Actually, what astronomers and physicists and chemists and biologists often do is that they make a graph of these things, right? Here, for example, is a whole bunch of hydrogen, helium, lithium, oxygen, carbon, nitrogen. Each kind of element has a different level of absorption emission spectrum. These are emission spectra. So you've got this sort of warmish background, and then you have this extra high energy gas, maybe in a tube or in a container or something, and you can see how they shine. Hydrogen, being the simplest atom, right, has one proton and one electron, has only a few lines like this. Helium has more lines because it has two electrons and two protons in its nucleus and two electrons on the outside. Lithium has three electrons orbiting a nucleus that has three protons, and so it has more lines still. Oxygen has 8 more lines. Carbon has 6, nitrogen has 7. So once you get to like above 3 or 4, you're getting lots of different lines, and every kind of thing does its own thing. Furthermore, you should know that hydrogen, right, and in this case, this is hydrogen atomic gas, right? These atomic gases sometimes are different from molecular gases. So O2 has a different spectrum from individual oxygen atoms that have not been combined into oxygen gas molecules, right? So each of these things tell you all different things about the matter that you're looking at. And then, as I said, astronomers graph these, right? So here is an example, the wavelength in angstroms, which we were talking about. Remember, an angstrom is 1/10 billionth of a meter, right? Red is kind of where the limit of our visible light red is, about 7,000 angstroms or so. And then purple is roughly the color at the other end of the spectrum where we can't see. That's about 4,000 angstroms. Short word of this is ultraviolet light. Long word of that is infrared light. And if I graph these, right, there's not a lot of light here, so it's kind of low. And then, oh, there's an emission line. So there's like a little spike of energy up there, intensity. And then here it's kind of growing in intensity. It's kind of brighter, but right there, ooh, there's a line. So boom, you have a little bit higher emission line. Then here higher, there higher, there higher. Right, there's 2 lines right near each other. This is kind of a fainter line and kind of a brighter line. So you draw that. And so this kind of graph gives you a sense of what elements are in here, right? This might not be the only thing. Maybe that line is produced by hydrogen. Maybe that line is produced by some other element. Maybe that line is produced, those 2 lines together are produced by oxygen. Maybe that line is produced by sodium. All of this allows us as scientists to know what we're seeing, right? So if I want to look at a mysterious object, far away, or I'm looking at maybe some DNA, or I'm looking at a star or something like that, and I can't quite figure out what it's made out of, because it's hard to do that kind of thing in some instances. But if I look at the light pattern, the spectrum that comes out, thanks to quantum mechanics, I can tell what atoms are there, what molecules are there, what percentages they are, maybe what temperature they are, maybe how fast they're moving, maybe all kinds of different things that are involved. What is their chemical reaction? What kind of magnetic fields is it experiencing? That stuff all comes out of these energy levels, right? Because they're allowed by this wave particle duality and the constructive and the destructive interference and all those different other forces getting involved in turning this atom into this beautiful system that's affected by all kinds of things in specific quantized energy levels. Wow. I don't know if your mind is as blown as mine is every time I talk about this, but you realize that what we know about the universe, our understanding of all of these things here, is fundamentally defined because atoms and molecules have this quantum physics stuff that it's involved with. And because of that, the nature of what we see from them, the light that they emit, heck, even like the vibrations they have, the heat, the temperature that we were talking about earlier, right? I remember earlier in the semester we were talking about different states of matter and phases of matter and how much energy. All that stuff is tied up into the quantum mechanical nature of matter and energy. And as a result, we think about the deepest things, about like atoms. What are we made of? The chemistry, right? The DNA, the proteins, all those things. The quantum stuff is all knit in there in our minds. Maybe I'll leave with this for now. We'll call this the end of this lecture for now. There's still lots of cool stuff to learn about quantum mechanics, but we're going to, like I said, transition over into atomic physics, because this is atoms, right? And since we're made up of atoms, the ability to manipulate atoms, break them apart, stick them back together, that is a huge part of our society today, right? It's a huge part of our existence and our technology. To be discussed in the next lecture. I don't want to jump ahead, but let me finish this lecture with the concept of quantum mechanics in our brains, in our minds, right? We talked about this a little bit already, but electrical impulses, little tiny voltages, are what make the difference, that what send the signals, that what pass information along our nervous system, in through our brains, down our arms and legs and spine, out into our fingers, all the things that we communicate with, right? The reason I'm able to wiggle these fingers, because my brain is telling my body through all these different things. All of that happens because there's tiny amounts of electricity flowing through our bodies. Those electrons, right? They're not bound up always in like big elements, atoms and molecules and stuff. But when they're tied up there, or when they're loose, or when there's photons going on, when light is coming in, all that, the electrical signals in my body are affected by quantum mechanics, right? In large signals and so forth, they all work sort of on average in a generally very smooth and predictable way, right? These tiny voltages are about 70 milliamps or something like that. So not very big, but they're certainly bigger than sort of individual electrons. But there are individual electrons zipping around. There are small groups of them. Sometimes when you have a single nerve cell, there are electrons that are doing funny things. They are uncertain. That uncertainty may actually lead to creating things that we didn't know before. This is stuff that we're not really sure yet. This is at the frontiers of modern physics. But really, could quantum mechanics be the thing happening in our head with all this different quantum tunneling, with all the different pieces of energy flowing in and out in ways that we can't completely predict, but are quantized and have certain predictable levels on average, right? Can we possibly ascribe those kinds of things, that randomness, yet within a well-prescribed sort of set of rules, Could that, chaos within that rule set be the origin of what makes our minds different? That makes things like creativity happen, things like innovation, things that we wonder about. Like, why do I say something different from you do it? Is there something that I can think of? Do I create things? Do you create things? When you do art, is that because you do it differently? Because your brain, which otherwise follows the same rules that my brain does, has just that little tiny difference in the quantum mechanical aspect of the energy and the particles moving around that make things different? Is the emergence of things like consciousness, self-awareness, intelligence, creativity due to quantum mechanics? Pretty cool, right? Fun stuff to think about. I want you to do more of this stuff later as we're talking in the quantum mechanics study guides for lecture 20. I hope you've been filling out study guide already up to this point. And overall, just remember, this is great stuff. Watch the videos, do the very, very small calculations that we're doing, a couple things here and there to understand, right? Just to remind us, right? The particle waves and matter waves of de Broglie, the Compton wavelength, when you have light and matter interacting with one another at the most basic particle to particle level, and then the uncertainty principle stuff that you've already been doing in the previous lecture, right? Wow. The quantum tunneling stuff has just begun. The atomic physics, quantum tunneling is everywhere. All right. And not to mention this nuclear fission, nuclear fusion stuff. That's the next stuff. The next few lectures are going to be about that. Wow. Thank you so much for your time. I really, really appreciate it. Thank you for your energy in learning all this great stuff. We'll talk again in the next lecture. Fill out those study guides. Ask any questions of me or your recitation instructor. If you have anything you want to ask, happy to answer. Thanks so much. See you in the next lecture.